Well, thank you for joining us today. We are with some senior members of the Infleqtion software team, all of whom, by the way, are in Chicago, in case you were wondering. And the topic for today is extreme optimization for quantum computing using Superstaq. Superstaq is a software product, as we'll discuss today, for quantum computers. This topic of software, and especially quantum software, is near and dear to my heart. So I really welcome the opportunity to talk to these folks today about it. And I think to these folks, we're really going to have to justify this word extreme, right? And what we're talking about. So we'll be talking about Superstaq, of course, and we will get a little bit technical at points. So I'll try to highlight that because there's some very low-level optimization that has to be done for us to really reach the so-called practical quantum advantage, right? Where quantum computers and classical computers can do much better than just classical computers working by themselves. So let's bring up the list of who we have with us today. To formally introduce myself, I'm Bob Sutor. Up until 3 weeks ago, I was with Infleqtion. I then joined the Futurum Group, which is a analyst, consulting, advising media company, and I am a vice president and the practice lead for all things quantum, as well as AI, enterprise AI, advanced AI topics. Next, we have Dr. Pranav Gokal. He's the vice president of quantum software. Victory Omole, who is the senior quantum software engineer here, and Stephanie Lee, the quantum software manager. Stephanie will tell us a lot about the product and what we can do with that. So the agenda today is about Superstaq, and we'll be defining that. So Pranav will start us off in a moment to talk about, well, an overview, but also some announcements. Real people are really using Superstaq today, and they're using it on a variety of hardware. And the team asked me to make this point really clear. Even though Infleqtion is doing quantum computing, the Scorpius program, this software runs on quantum computers of several different modalities, and you'll see examples of them through each. And we of course would love you. They would love you to run Superstaq on your hardware of choice, and we'll get to that. We're going to show Superstaq in practice. That is, aside from just the what, we'll be showing you some details and really trying to answer the why. You know, it's nice, and frequently people show products and they just go up there and say, isn't this wonderful? I have this great product. Well, why did you come up with it in the first place, right? What are the use cases, but why do people care? And that's, I think, should really convince you on the focus and the importance of what is going on in Superstaq. What's next? The team is working on a few additional topics. Of course, as quantum computing goes on over the next several years, there's never going to be an end to the amount of software that people do for them. But what's on the immediate radar? And Pranav will talk about that. Stephanie will come back and tell you how to learn more. And then we're going to open it up to Q&A. So there is a Q&A button there for you, at least for me here on Windows. It's on the bottom. You can ask your questions. I will keep an eye on them. Maybe we'll address some of them as we go along. Otherwise, we'll take a look when we're done with the main conversation. You can think of this as kind of a panel discussion or a conversation driven by a few slides. So you'll be seeing me a lot as my colleagues here jump back in to address certain things. All right, so let's get going. So Pranav, you lead the program. Why don't you start us off with an overview of what Superstaq is, and why does anyone need something like Superstaq?
Great. Thanks for that intro, Bob. So Superstaq is our flagship quantum software platform. There's a stack for quantum software the same way there's a classical stack, and that stack has different layers. There's the application at the top, there's the hardware at the bottom, and there's multiple levels of middleware in between. The core philosophy of Superstaq is all about performing extreme and very deep optimization, not just in these specific layers in each part of the stack, but actually across the entire stack. And what this amounts to is a product that we've built that has compounding advantages as you climb up and down the stack. So we do things like very optimally decomposing and running programs on underlying hardware, very advanced error mitigation to reduce the impact of noise, and primitives for enhancing the execution of quantum programs at large. And oftentimes, the best analogy I can think of what our ambition here is basically to do what CUDA has done for NVIDIA GPUs. We want to bring that same level of attention in the software to QPUs, quantum computers. So, in a nutshell, that's what Superstaq is about. And I think it's worth noting and perhaps foreshadowing that the pathway that we're on is helping to plant seeds for this next generation of quantum computing that our field is entering right now, which is the era of quantum error correction. And we're going to talk a little bit more about that, but I'll just foreshadow that everything that we're doing today helps the long term and the near term future of quantum computing, all delivered through a cloud software platform. And in brief, that's Superstaq.
So Pranav, here's a question. So if I were to pick up a quantum computing book of some sort, I'll see circuits and I'll see X, Y's, and Z's and Hadamards and C naughts and all this sort of wonderful stuff. And maybe I'll learn about some algorithms. I'll try to break encryption with Shores, maybe someday. Um, what does Superstaq do? I mean, I can write the circuit. Why do I actually need something like Superstaq to go from the circuit I see to what really runs on the different varieties of quantum computers?
Yeah. So, for instance, you mentioned the X, Y, Z, maybe H, and C naught gates. These are all gates that we'll find in the standard textbooks of quantum computing. And they're very useful, perhaps, as educational tools, ways for us to attempt to wrap our heads around quantum computing and quantum mechanics. But the reality of what happens on underlying hardware is very different. There's never a button that does an X gate. And in fact, this is different from the classical world where there is a button that essentially does a NOT gate in hardware with a transistor. And so it's a very different scenario in quantum computing, what happens under the hood. And what Superstaq does is it effectively goes below that sort of textbook educational layer to get high optimization, extreme optimization at the level of what quantum hardware actually runs. So that's what we're going after for Superstaq. Now, of course, for many of our users, they want to, in fact, perhaps most of our users want to write software at the level of textbook implementations of here's a blueprint for Shor's algorithm, here's an X gate. And we support that at the top of the stack. It's just that the bottom of our stack is able to synthesize and decompose much more to the low levels of hardware.
Just to give a classical analogy, long time ago when I started programming, we had to hand optimize our programs. We had to know what the computer architecture was. And we would make different choices about how we wrote the code so it would run really fast. And then at some point, they said, Stop doing that. The compiler can do a much better job than you think you can." So we're already at that stage, I would say, right? That there have existed quantum compilers or transpilers for a while, but this, to use the phrase from the title, this extreme optimization is really to eke out the most from your hardware, given the intent of what the user is trying to do. Well, you've had a couple of successes here. Can you tell us about those in terms of
Yeah,
clients?
sure. Well, maybe to start off with, we're really excited to share two announcements today. The first one is with the Department of Energy, and this is our first time publicly mentioning it. So it's $1 million headline, which is that we have been selected for a $1.2 million Phase 2B SBIR award. And this is following on to Phase 1 and Phase 2 programs that we executed with the Department of Energy to support the development of Superstaq and support commercial outcomes of that development. So for those who may know, the SBIR program supports small businesses that are working on cutting edge technologies and getting them kind of outside of the research stage into the commercial stage. So this is very competitive as a program, but also a really fantastic way that we wanted to further this development. So happy to share that news today. And we're going to first talk a little bit about some of our interactions with the broader DOE community, which has been leading the way oftentimes in the US for quantum computing. A second partnership that we want to highlight today is just last month, we announced Defense Cyber Marvel 3 and Infleqtion's participation in this event. And yesterday and this week at the NVIDIA GTC conference, our partners at NVIDIA have been highlighting what we've done with Superstaq in integration with the QU Quantum and CUDA quantum ecosystem at NVIDIA. So in short, what Defense Cyber Marvel 3 was is Europe's largest cybersecurity exercise that spans all of NATO, took place in person in Tallinn, Estonia this year. And we were able to deploy Superstaq to hundreds of cyber specialists across NATO militaries to essentially explore a cybersecurity advantage called super.tech, a lot of supers. But in any
Okay.
case, one of the cool things about Superstaq is we're deeply integrated into simulation tools that run on top of NVIDIA's ecosystem. And that's one of the exciting areas where we're finding that quantum technology is intersecting GPU and cybersecurity best practices.
Just a historical note, Infleqtion, then called Quanta, bought your company, Supertech, almost 2 years ago now. So hence all the supers, right?
That's right.
Stephanie, let's move on, talk a little bit more about improved performance. Want to show us this? Yeah, can you explain this chart to us?
Yeah, definitely. So the story behind this is probably a lot of people who've joined to watch know about the power of quantum and quantum applications. A lot of those applications are coming on sort of fault tolerant, perfect quantum machines, which is something we don't have right now. We have sort of error prone, noisy hardware. And there are, I think, two paths to sort of get to that perfect quantum hardware. One is through years and years of hardware improvements. And the other path, which is the one that we are on and believe in, is to couple those hardware improvements with software improvements. And those software improvements is where Superstaq comes into play. So on this graph, you'll see this viable quantum computation frontier. This is where we think current hardware is without Superstaq, and sort of these dots are the applications that we think that hardware can be useful for. And then this extended frontier is where Superstaq comes into play, and it improves the error rates on current hardware so that you can capture more of these quantum applications. And this sort of 10 times better, that's where we think our baseline performance improvement is. And we'll go into this more a little bit later in the slides on what sort of improvements you can see with Superstaq on various types of hardware.
And this is part of what I started by talking about with the practical quantum advantage, right? If you just chug along with hardware, with let me say basic software and so forth, eventually we'll get there. But software like Superstaq has the potential of pulling this time in when we might really get practical use cases, right? Quantum computers working on practical use cases.
Mhm.
Now, Stephanie, the title of your next slide is a little controversial. So as we go to this, uh, let me say a little bit about your claim of no quantum software expertise. Well, first of all, you don't have to know physics. I'm not a physicist, which is usually pretty obvious pretty quickly, I must say. But if you know Python and you want to jump in using something like qiskit or cirq, what are you telling us here about how you would really use Superstaq? Is it difficult?
Yeah, that it might be controversial. I guess to qualify, it's no sort of low-level optimization types of expertise needed to be able to use Superstaq. Here we're giving sort of a very simplified example, but all of our programs sort of run in this pattern. The first thing you can do is you can either use qiskit or cirq with Superstaq. You'll then choose a backend. You'll create your quantum circuit, and then very easily you can run your job and get results. So you might need to know what a Hadamard is. You might want to know what your circuit looks like. But there's a scarcity of sort of this like really deep knowledge of quantum software and how it connects to the hardware, and that's sort of where we come into play.
So no low level phase optimization just to use Superstaq,
Yeah.
right? Okay. All right, well, that's good because I'd be hopeless. I do like, by the way, the support for both Qiskit and cirq. I mean, together, they're the vast majority of platforms that people are using for coding today. Customers and partners. Pranav started us with a couple of announcements of what's happened recently and what's going to happen. Can you tell us about these folks?
Yeah, definitely. So we've had a lot of customers and collaborations in the past few years. Uh, I would say this slide captures two sets of customers. The one that we'll focus more on later in these slides is these academia and national labs. So you'll see Sandia, Argonne, Berkeley. And then the next set of customers are these application-based industry partners. One example here in the corner is JP Morgan. We recently released a paper called QChop, and I will link that paper later in the slides, but that's an example of an application that quantum computers can be useful for. We won't dive too deep into the industry side. We'll stick more with the academia. But yeah, both sets of customers we've had really good relationships with in the past and currently ongoing.
Okay, and by the way, I've just noticed we have several questions in already, so keep them coming. Um, all right, now we're going to start getting a little bit more technical. Pranav, we're going to turn to you here. So dynamic decoupling, it's not sort of some kind of new wave, Hollywood way of getting divorced. I know that. It does apply to decoherence, though. This problem that once you put a quantum state in a qubit, it doesn't stay there forever, and therefore errors start getting introduced. So what can Superstaq do using dynamic decoupling to reduce the number of errors?
Yeah, so indeed, we are going to get a little more technical here, and the analogy to Hollywood divorces for dynamic decoupling is a good one, but it's something different for the hardware physics of qubits. And as you pointed out, qubits have short lifetimes and error rates that accumulate over that lifetime. And under standard compiler techniques, you just kind of have to deal with that, but it really limits the performance that you can get out from quantum hardware. What we've been able to do is engineer a very specific way of having something called dynamical decoupling pulses, which you can just think of as sort of a protective layer around a qubit that can dramatically extend its lifetime. So for instance, on IBM's superconducting quantum bits, we've deployed a set of dynamical decoupling techniques that achieve maximal enhancement of the lifetime of a qubit without incurring extra what's called crosstalk, which is interference between different qubits. Now, the bottom line here is when our users use Superstaq, they're able to get much better performance than they otherwise would get either without dynamical decoupling techniques or with suboptimal dynamical decoupling techniques that exist in other software stacks. So for instance, with the IBM Brisbane 127 qubit machine, we ran a prototype quantum application called GHC, which in short is the best test of entanglement, perhaps the most quantum feature there is out there. And what you're seeing on the screen is a comparison of what Superstaq delivers in terms of performance versus what the leading platform otherwise for doing this, IBM's own runtime platform, can achieve. And in short, we can get here a 15x advantage in the quality of the result. This is not a panacea. It doesn't completely zero out the noise, but it does mean that you essentially get the key characteristics of the ideal output in real hardware, whereas otherwise that's pretty much impossible. On our downstream users, to give an example here, one of our customers is Argonne National Laboratory, and they've leveraged this technique of dynamical decoupling using Superstaq to achieve a record for simulating the water molecule, as well as the methane molecule and so forth on real hardware. And that's now in published work. So this has been one of our early successes, just published last year, but the first results came out 2 years ago with Superstaq. And because we're running this on a 127 qubit machine, we're very excited to take this to the next level on molecules that are much larger, things like the caffeine molecule or the cholesterol molecule, or perhaps biopharma relevant molecules. And because we can run on these large platforms, we're eager to work alongside partners who want to start exploring this utility scale era of quantum computing.
Pranav, with this work on other quantum computers other than, let's say, IBM superconducting, as long as they have, 15 qubits, thinking of this experiment in particular.
It does. And in fact, one of our other key wins with dynamic decoupling has been on Rigetti's platform. That's also a superconducting platform, but we have this nice blog post with Amazon Web Services where we showed off what dynamic decoupling through Superstaq can do for that platform. And in
Mhm.
fact, every platform we support, I think we're going to talk later about trapped ions, and of course, we have neutral atoms in-house. They all can take advantage from dynamic decoupling, and indeed, Superstaq does that job of tailoring dynamic decoupling to the hardware backends.
So we can relate this directly to a benchmark, really, right, for quantum computers, to see what the machine does natively, and then as well as seeing how it can be optimized by Superstaq, or if you have competitors, right, to
Yep.
see how well it might be done. All right, Victory, let's turn to you now. So Victory is a let's say senior quantum software engineer. I want to make sure I got the words right. Now, Victory, before we even get started on your bring your own gates, um, I was very pleased last year. I taught a seminar on quantum computing, and Victory, you were a guest speaker, and uh, the students loved your presentation, particularly when you explained what does it mean to be a quantum software engineer. It's not one of these titles that, first of all, there are a lot of people who do it. But could you just spend a couple of minutes, explaining what that is and how you got to where you are? Somebody has to use all this software, right? And it's going to be folks like you who are developing and using it. So could you take a couple of minutes and just give us a little bit about your background there?
Yeah, sure. I'd be happy to. So yeah, quantum software engineer is a combination of, like, of course, like, people know what software engineers do. They program um, computers. And what a quantum software engineer does is the exact same thing, but we program quantum computers instead. So um, this is something that I've been passionate about since I was in college. And yeah, so I have a lot of fun with it. Um,
And you did pretty well with cirq a few years ago. Could you remind us about the award you got regarding cirq?
Yeah, so I won an award for open source contributions for cirq back in 2022. So I'm an active contributor in the cirq community.
That's right. So once again, it's even though a lot of these examples are qiskit, it's a well-balanced approach to making Superstaq available. Okay, so now bring your own gates. I don't think a lot of people may not realize that, quantum computers don't all operate the same way, independent, even though they have modalities. They have different, very low level core gates. And oftentimes those gates look extremely strange. Pranav, you and I were talking about that before, about what you actually compile down to. So is that the sense in what you mean about bringing your own gates, and what are we doing here? Oh, and by the way, I want to a note on terminology here. We've been talking about qubits. So qubit has two quantum states, ket0, ket1. A qubit has three, right? And a qubit has n. So I think those should be qnits, but nevertheless, they're qdis. So that's just a couple of terms you use on this slide. Could you tell us what Superstaq is doing here?
Yeah, so uh, before I start, I want to tie in. So Berkeley Lab has this a program called AQT, which stands for the Advanced Quantum Testbed. It's a superconducting quantum computer, and we collaborated with them to do this experiment where we did the first ever implementation of two Q-trit swap operation. Q-trit is like the quantum analog of like ternary logic in classical computing. And as you can see on the diagram, um, we have we show that the swap gate is actually working. So if you look at the 0.83 blue square, if you go down, there's 1, 2, and then if you go to the left, there's 2, 1. So that swap operation is 80. It's successful. The fidelity of it is 83%. And so basically, the more blue, the better, in the sense of that it shows that our swap gate is working correctly.
Okay, so good translation, high fidelity translations to the native gate supported by the hardware. Um, Now, noise is a fact of life with these physical qubits, no matter where they come from. So on the next slide here, you did something with QSCOUT and Sandia. What's happening there?
Yeah, so QSCOUT is this same type of program as AQT, but this one is an ion trap quantum computer. And this just shows building off what Pranav said about what Superstaq does, where we know a lot about the low-level hardware details of QSCOUT. That means we can do we can build targeted compilers for their machine. In this case, we used two techniques to demonstrate how to run circuits that are less error prone on their hardware. In one case, we did this application called swap mirroring, which gave us a 17% reduction in pulse amplitude, and that resulted in fewer errors for the circuits we ran.
So here you're talking about swap gates, which need to be introduced at different times, depending on what operations you're doing with different qubits and how far away they are from each other. Right?
Yep.
Okay. Stephanie, I just want to make a note. One of our viewers here has said, way back to our quantum expertise slide, maybe it's no quantum hardware expertise that we should really be pointing out. So I think that's a good comment. And thanks for the contribution. All right. So what's next for optimization? Well, people will keep inventing new hardware. They'll keep optimizing their hardware. We have a fair number of modalities that people are working on. Also, people are just getting smarter. I mentioned before about optimization classically. Just let the compiler do it. Well, the same is happening with quantum compilers today. There are multiple levels to this optimization of the code somebody writes and what actually runs. Some are very high level optimizations for any target. I know that is, don't do stupid things, right? It fixes those. And others are very low level based on the chip that you were targeting. It could be Intel, it could be power, it could be anything else, and so forth. So let's now look at what's next. So Pranav, we're going back to you. Tomog there, it's a short for tomography, which immediately reminded me of, well, what we used to call CAT scans and are now called CT scans, computed tomography, which most people don't do every day, at least the process of tomography. So what is tomography as it affects quantum computers, and what are you showing us that Superstaq can do better?
Sure. So tomography is part of a broader set of techniques in quantum computers that it's a mouthful, but we call QCVV, quantum characterization, verification, and validation. In short, what the heck is my quantum computer doing? And it turns out that QCVV, of which tomography is a subset, is much harder than what meets the eye. And indeed, medical tomography is already hard enough, but with quantum states, the same things that make quantum computers potentially exponentially more powerful for practical applications also make them exponentially more challenging to do tomography on. If I want to know exactly what state my qubits are in, I have to do an exponential number of repetitions of tomography measurements to understand that. And that's not a problem at 1 or 2 qubits, but it actually rapidly becomes a problem at the 3, 4, 5, 7 qubit scale. And to give an example here, what you're seeing in that circuit is for a quantum error correction code known as the surface code. It's the smallest example of quantum error correction with that code there is. And if we want to understand how well is the 7 qubit circuit running, tomography would require us to take hundreds of thousands of repetitions, or called shots, on quantum hardware. And that's very expensive and basically undoes all of the great exponential advantages that quantum computing would otherwise offer. So that's a problem. And you'll notice, for instance, there's a log scale on the y-axis there. What we've introduced is the first commercial instantiation of something called DFE, which stands for direct fidelity estimation. And this is basically a trick that leverages an important principle of something called Clifford circuit simulation, which details of that are not terribly relevant here. But the point is that we can actually get an exponential improvement for QCVV, that is verification of certain quantum states like the one on the screen. So instead of needing hundreds of thousands of shots for the 7-qubit circuit, we would only need a few 10 or a few dozen shots to verify that this quantum circuit is working as intended. And what's really nice here is that we're now entering this era of quantum error correction with logical qubits. What that really means is we're going to have dozens, if not hundreds, if not thousands of physical qubits that we need to understand what sort of errors are happening. Are they working as intended to make sure we can run the applications we want to? And that's where DFE is very important. And it fits in a broader set of initiatives that we're undertaking as part of this $1.2 million DOE award to advance the state of QCVV and bring it into its first commercial implementations that quantum hardware users can use. So in short, this is about verifying that as we build larger machines, they're doing what we expect. Turns out that that's a really subtle task and a hard task with tomography, but we're building tools that makes it efficient.
So quantum computing, sometimes exponential is good, sometimes it's bad. And
That's right.
you worked around this. Software like this is really important. I feel that we're now well beyond the initial phase of quantum computing, right? It's been years since people could first really use quantum computers on the web. And so, as you pointed out, we're now starting to get hundreds of qubits, thousands of qubits. We're starting to get logical qubits. The game is changing rapidly. So things that worked well with small systems just are not going to make it. And this is a great example. And I think this is an example as well of the next generation of software that we will need. Okay, so we promised to talk a little bit more about error correction and fault tolerance here. Victory, tell us what you're doing here. And you and I spent an awful lot of time discussing this graph here. After you give an explanation, walk us through the graph and what are you really explaining here that Superstaq, what's the advantage that Superstaq is giving us?
Sure. Yeah, just to tie it back to Stephanie's slide, where she showed the graph of how Superstaq extends different tier 2 applications. So you can only go so far on the kind of applications that you can reach without using error correction. But there are some applications that will really need error correction, like a Shor's factoring algorithm. So that's why the Superstaq has been working on implementing features that allows us to compile applications into the error corrected versions. And we've simulated these circuits on for Quantinuum's simulator. And this can also be applied to any other type of hardware, like the ones that we've been talking about. So in this graph, we ran an application for different types of physical error rates on a simulator. And we were able to study how our error correcting code behaved under these conditions and plot the logical error rate that we got from running these circuits. So basically what we're showing here, like the shaded area basically shows the part where we're under break even for error correction, where it's called the threshold. We're under the threshold, where we're correcting more errors than is being created.
Okay, so error correction, well, it's the next big thing. I mean, it's what people talk about all the time, and it's what will bring an end to the so-called NISQ error that we're in, noisy intermediate scale quantum here. You can't just apply it to anything. You can't just have a bunch of very noisy bad qubits, right? And just expect to error correct them. You have to have them at least good enough. So what you're saying is that given reasonably good qubits, but not quite as good qubits as you need, Superstaq can help get you over that threshold. So you can actually start really creating logical qubits, doing fault tolerance, doing error correction. Is that right?
Yeah, exactly. So fault tolerance is, you want fault tolerance. There's the point that there's where if you look on the non-shaded area, you're doing error correction, but you're not fault tolerant because you're just not correct. Your error worsening instead of error correcting, basically. And then on the left, you're actually error correcting.
I also want to know, which is just a personal thing with me, is we really need an industry standard definition of logical qubit. We don't have to do that today, but I've seen it used in at least 3 or 4 different ways. Is it error detecting? Is it error correcting? How many errors does it correct? And so forth and things like this. So those of you who are out there, this is a task that someone will do pretty soon, I suspect.
Yeah,
Steph?
that's a really great point. Yeah, I'll just say how we define a logical qubit here. So a logical qubit is what we ran. The physical array we did was we did random bit flips and phase flips on our logical qubit. So we ran an error correcting code where we used many physical qubits to encode one logical qubit, we just kind of threw errors at these physical qubits, and we study how well our error correcting code was correcting the errors that were being applied to the physical qubits that were used to encode this logical qubit.
So I think the mental idea is you start with one qubit and you use a collection of other qubits to somehow correct any errors that occur in that first one you had. So a logical qubit isn't like one unit, one thing I point to. I mean, maybe manufacturing wise, it's a collection of qubits. I almost think of it as like a virtual type of qubit. It's not a physical thing. It's a virtual collection of things that behaves like a qubit, acts like a qubit. It's just the error rates are especially low, very low.
Yeah, virtual software, quantum software. That's the connection, right?
That's right. Not perfect, but darn good. All right, Stephanie. Now, how can people learn more about Superstaq? How can they engage with you? And how can they find out how much this thing costs?
Yeah, definitely. So I have my email here. We'd be really thrilled if you guys sent over inquiries, and you can send it to my email. I'd be happy to talk about pricing models, as you mentioned. I'd be happy to share the slides, go through any live demos, anything like that. If there are unanswered questions after this webinar, I'd be happy to answer them as well. On this slide, I also have the QR code for the QCHOP paper that was in collaboration with JP Morgan that I mentioned earlier. So that's sort of on the industry application side, where we've been talking, on the other hand, more about the academia low-level optimizations. And then these 2 pictures. So here is a screenshot of our documentation site. Here's the URL right down here. You can see tutorials for a lot of the content that we've talked about. So there's an AQT notebook, there's a dynamical decoupling notebook, there is a QSCOUT notebook, so you can sort of check that out on your own. And then behind this photo is a screenshot of our open source repo called Client Superstaq. So you can contribute if you'd like, or just browse through that. That is on GitHub. So this is sort of what we have in terms of if you would like to learn more about Superstaq.
Okay, very good. Thank you. And Infleqtion has a couple more webinars coming up, Stephanie, regarding quantum computing, but also more generally, it's from the company. So bringing in atomic clocks, quantum sensors, RF, and so forth. When are those?
Yeah, definitely. So we have 2 webinars coming up, one in April and one in May. The first one on security, defense, and aerospace, and the next one on enterprise. You can register for these events at this URL. That QR code in the corner will also get you there. We'd be happy to see you there as well.
Okay. So now let's turn to some questions. We have some from the audience, and I also want to say thank you for answering them among yourselves and qualifying. That's good. It's a nice little community. Why don't we start, just for the sake of let's catalog the modalities. Not to talk about, but so far, which of the quantum computing modalities have you worked on with Superstaq? So things like superconducting and so forth. So Pranav or Victory, which are the ones that are included so far?
Yeah, sure. So we've published results from Superstaq applied to superconducting qubits. That's, for instance, IBM Rigetti Advanced Quantum Testbed, trapped ion qubits. That includes, for instance, the QSCOUT platform at Sandia, Quantinium, have some work on IonQ as well. And then, of course, neutral atom, we have our Scorpius program in-house, which is building neutral atom quantum computers. We have also done some in-house work on silicon spin qubits, and you should expect to see some upcoming papers on that as well. So pretty much any sort of qubit modality that is based on gates, we support.
Right, I was going to ask you about that.
Just to add on to Pranav's answer,
Sure.
as quantum software engineers, it's basically any hardware we can get our hands on, right? We are excited about new hardware, and if you have hardware, please let us know, because we're always excited to program a new machine.
So going back to bring your own gates, bring your own hardware, right?
Yeah.
So Pranav, you made an important point, which is the gate and circuit model and the ones you described. So this is the digital quantum computer model versus analog, and not annealing for this here.
That's correct. This is the gate-based model, and that's the one that has the well-known path to quantum error correction.
Okay, all right, and that's an important distinction. Okay, let's see. So let me just kind of scan this in terms of questions. In terms of manufacturing, someone had a specific question about the manufacturing industry. Right. So this is much more open-ended. This is much more just thinking about eventual applications. What industries have you worked on? We've seen a couple names here. We saw Morningstar, we saw JP Morgan. Can you maybe riff a little bit on quantum computing use cases that you will see in some of these industries? Perhaps not the usual ones, if you will, but something like manufacturing. Where might quantum have a play here, and therefore where might Superstaq actually make those applications run sooner and better?
I'm happy to start that, and I welcome comments from Stephanie and Victory too. So this JP Morgan Chase paper that Stephanie had linked to earlier, that was a constrained optimization solver that we developed together. And in fact, the genesis of that paper was an interaction we had with BMW through a quantum computing challenge they ran a couple of years ago. And BMW was looking at constrained optimization for their manufacturing processes. So there's a fair amount of research and development and POCs taking place that is about where manufacturing processes could leverage quantum solvers, especially also if there are chemistry or chemical manufacturing centers that could benefit from direct molecular modeling. Those seem to be very hot on the radar of where emerging quantum computers intersect practical business use cases. I think that's part of what I'd highlight. The other thing is our platform that we're describing today, Superstaq, is quite agnostic to the specific types of applications. At some level, we take in a application and then get as much juice as we can, or as much mileage as we can from existing hardware. And so we like to work with any use case. Manufacturing has some specific prototypes that we've developed, but at some level, most quantum programs come down to the same primitives, which we've gotten good at optimizing through these years of software development. Anything to add, Stephanie or Victory?
Yeah, so in the biomanufacturing, just to add on to what Pranav said about the flexibility of Superstaq, I mentored a team for a hackathon at last fall, which we won for the technical challenge, by the way. It was a problem by CSL Bearing. It was a biomanufacturing problem for particle packing, where the team actually used Superstaq to get their challenge done. So that's just an example of how Superstaq has been used for manufacturing problem.
Couple of tricky questions here. So how would you say you compare to other similar optimizing software without naming names? Okay, but you're not entirely alone in this field. What advantages do you bring here? Either in the software, what you'd consider your team, the background. SuperTech, we mentioned before, was a spin out of the University of Chicago. So what makes you special? That's a strange way of stating it, but you get the idea.
I can start with a quick, sort of higher level overview. I think you did touch upon a lot of what makes Superstaq special and our team special. I mean, through these slides, you've seen sort of like the statistics. I mean, the performance of Superstaq is really impressive, and we've, internally benchmarked against, a lot of compilers that are out there. So that's sort of one side, the more technical side. Maybe Pranav and Victor, you can touch more on that. And then I think on the other side is the actual interactions with our team. I think a lot of our customers have really enjoyed the collaborations. If you go to our website, you can see a quote from some of our users. One is like on QSCOUT. I think they've really enjoyed the back and forth that they have, sort of the discussions that they have, and the new research that has come out in the quantum community, both in tandem with our collaborators and with our team. So that's what I would say is like a really high level. And personally, as someone who works with our team day to day,
Mhm.
they really are a great group of people. So would echo the quotes that you see on our website.
Okay.
I would say we're probably one of the most open source friendly quantum software companies out there. Just based, like we talked about the award I've won for like open source software contributions, and we still do continue to actively participate in the open source quantum software community. So that makes us unique as well.
You recently released something in open source about error correcting codes. Can you describe that?
Yes, so we released a library called QLDPC. It stands for of course, quantum low density parity check codes. Pranav actually talked about it at the corporate webinar. Maybe you can add on to what it is.
Yeah, and in fact, I can perhaps in tandem answer this nice question from Evan Dobbs in the chat. So this QLDPC library is about the analysis and design of a new class of quantum error correction codes. This library is totally open source. And what's really cool is that these error correction codes change longstanding assumptions about how many physical qubits are needed for each logical qubit. Historic estimates have been as aggressive as there needs to be 1,000 physical qubits to make one logical qubit, which is quite expensive. And now with QLDPC codes, we're seeing opportunities to have just 10, 20, 30 physical qubits for one logical qubit. So we do have an initiative to compile directly to those QLDPC codes. What we have right now to share with the world open source is this environment for people to come sandbox codes, inspect previously discovered codes. And in fact, one of our upcoming results that we'll share is that we've actually found new results that are perhaps surprising about previously discovered codes that the software library has enabled. So indeed, there's high integration between our Superstaq efforts and these quantum error correction codes.
And the work that Victory described about the logical qubits versus the error qubit rate plays right into that as well. Because once again,
Exactly.
the lower the rates, the more applicable and the fewer qubits that you need as well. If I were a quantum hardware vendor and I wanted to work with you, well, I know to call Stefan. Okay, so first of all, um, there might naturally be this little concern saying, well, you just described all these other people you're working with. How do I know that if I work with you, you won't take our joint IP and just hand it to my competitor? That is, give me some confidence here about the way you actually work with competitors in the industry, hardware competitors, to keep everything nice and separate, and allow them to get the, if you will, the advantages that they're partnering with you to get specifically. It's a little bit of a rude question, but I think it's one sometimes people have in the back of their minds.
Yeah, maybe I can touch upon that. At a high level, internally at Infleqtion, we do have a firewalling process when we need it. So that's just to keep communication channels between the people who need to know, who are working on the project, and we keep that information away from other people who are perhaps like working on different types of projects at Infleqtion. So that's something that we've definitely implemented in the past, and can definitely do in the future with different types of hardware vendors.
And I do know, and I come from a commercial background before Infleqtion. I was with IBM for many years, and of course, we always had to separate projects, particularly when you have a services organization. You work with competitors all the time. So let me say as a partial answer to this, this is not new. Somehow this is, the situation is not new just because it's quantum. People know how to do this. But also when you work with the government, a lot of times the projects you work on may be classified. So, these firewalls that you mentioned, Stephanie, are just built into the process. So point being, if I can paraphrase you, is clients shouldn't worry about this, and you'll make sure that what is theirs stays theirs, what is yours together stays that way.
We've so like even like our quantum hardware, like our glass cells are bought by our competitors. So it's the same thing with our software, right? Like we've already proven that we can we've firewalled stuff, like Stephen was saying, we firewalled stuff before, so we can do that again for software.
How would Superstaq work? So we've talked about a whole bunch of players here. You showed the IBM, so that's in your case cloud access, right? How would somebody on AWS or Azure Quantum use Superstaq? How would they somehow plug into that?
So many of these platforms, including both Azure and AWS, now have excellent support for qiskit and cirq. So the best way is to contact us, and Stephanie had our email address to set up kind of a live demo. We can do free trials as well, but there's nice ways to plug into the qiskit Superstaq or cirq Superstaq ecosystem and just call a compile object basically, and then pass that off to Bracket or Amazon Bracket or Azure Cloud and so forth.
Okay, and sometimes there's a little bit of exchange regarding tokens and things like this, identifications, and that you have to get straight, and that's why they should talk to you.
That's right.
All right, I think we're pretty much, we've touched on a lot of the questions which concerned error correction and so forth. Let me throw it open to maybe some closing comments from you. Victory, let me start with you, and then we'll go Stephanie and Pranav.
Yeah, thank you so much for attending the this webinar, and yeah, please contact Stephanie. And if you're interested in like more about the work we do, then yeah, we'd be happy to hear from you.
Stephanie, can they stop by if they're in Chicago and say hello?
Oh yeah.
Yes.
Just shoot me an email. But yeah, I want to just echo the sentiment that Victory said. Really happy that so many people have come here to join us for the webinar. Happy to answer any questions. I think we addressed most of them, but yeah, if there's any extra outstanding things, yeah, feel free to contact me, but thank you so much for coming.
Pranav?
I'll just mention that Superstaq has been a labor of love and has benefited tremendously from community engagement, from the support of the US Department of Energy, as well as other funders and partners in the ecosystem. So we're excited to take this next level, excited to announce the Phase 2B $1.2 million award and pave this path to the next generation of quantum computing as well with error correction through Superstaq.
Okay. So for all those of you, I know in the audience we have quite a range of people from low-level hardware implementers to students. For those of you who are relatively new to quantum computing, you may have learned qiskit or cirq or indeed some of the other libraries and SDKs out there. You may have started to learn about quantum computing, getting your hands on it, maybe done some course assignments. Now it's time to move to the next level. Right now, it's time to go beyond simply somehow representing the circuits in your textbooks or all these famous algorithms and things like this, but really start looking at what optimization means. And Superstaq is a great example of that. So thank you, folks. Thank you for giving me the chance to talk to you here today. This recording will be made available, and Stephanie, the slides will also be made available as well. So you'll all get some more information about that soon. So thank you very much. Thanks for joining us.